Okay, thank you, Professor Konto, for your very kind the introduction. Hi everyone, I'm Mitsu Okamura from Ehime University, Japan. It's my great honor to present my work as a keynote lecturer in this conference. I'd like to extend my sincere appreciation for the organizing committee to provide me this opportunity. The title of my presentation is The Factor Affecting Liquefaction Resistance and the Assessment by the Pore Pressure Model. I'd like to express my special thanks to a colleague and former student in Geotechnical Laboratory of Ehime University. The work presented here was financially supported by JSPS Kakenhi. So I'd like to spend some time to explain the background of this work. The resistance of sand to liquefaction has been investigated over several decades. Significant progress has been made in understanding the fundamental mechanism and influence of various factors on liquefaction resistance. However, assessment of liquefaction resistance on clean sand still involves considerable uncertainties, even in laboratory studies, and the effects of influential factors are still current topics of the soil liquefaction study. With regard to effect of shaking history, for example, it has been recognized that the cyclic weak shaking in drain condition enhanced the liquefaction resistance of sand. This shows the liquefaction resistance RL of sand subjected to pre-shearing. The drained pre-shearing of up to 10,000 cycles almost tripled the liquefaction resistance like this and like this. The result of similar tests in the literature consistently indicate that liquefaction resistance increased with number of cycles, as indicated here, and the cyclic stress ratio of pre-shearing, cyclic stress ratio in pre-shearing. The empirical relationship, some empirical relationships have been proposed, but none of the testing parameters alone quantified the increase in liquefaction resistance. The loading history, such as over-consolidation, has also substantial effect on liquefaction resistance. Empirical equations for liquefaction resistance were proposed as exponential functions of OCR, though the data point scatters like here considerably. The right-hand side here shows the saturation degree. This saturation degree also has substantial effects on the liquefaction resistance. This topic attracts engineers' attention in recent years, since the in-situ desaturation can be an inexpensive alternative of liquefaction countermeasure. The laboratory test results by many researchers were expressed in the relationship between degree of saturation and liquefaction resistance increment ratio. However, the data point scatters significantly like this, indicating that the degree of saturation is not the only parameters affecting the liquefaction resistance ratio. This is also the case for pre-shearing and over-consolidation effect. Empirical formula have been proposed for each effect, but none of them are sufficiently to explain the overall picture of sand resistance to liquefaction. The basic mechanism of the densification of sand and pore pressure generation in undrained condition, undrained cyclic shearing were conceptually demonstrated by Martin et al. 1975. The excess pore pressure generation, delta U, was clearly correlated with volumetric strain epsilon Vp. Recently, the attempts were made to explain the effect of factors using a unified single parameter of volumetric strain. For unsaturated sand, the volumetric strain owing to the increase in excess pore pressure has been found to be a dominant factor in liquefaction resistance. the liquefaction resistance ratio is uniquely correlated with volumetric strain during the undrained cyclic shearing. Regarding the pre-shearing effect, the volumetric strain accumulated by pre-shearing is also a factor that can explain the enhancement of liquefaction resistance. It may be valuable to go back to the basic mechanism of pore pressure generation and reconsider the effect from the fundamental principle. In order to do that, first of all, in this study, the pore pressure generation model is reconstructed in this study, which is based on the fundamental principle demonstrated by Martin et al. Using the model, the triaxial tests are analyzed to better understand the physical process of excess pore pressure generation that lead to liquefaction of saturated and unsaturated sand with and without stress histories. Finally, the attempt is made to explain the complicated nature of liquefaction resistance of clean sand using the unified index of volumetric strain using the model. This is the content of this presentation. The background and the objective of this study were already described. And the pore pressure, next is the pore pressure generation model briefly explained, and effect of the factors on liquefaction resistance are discussed. The principal model. When the sand is subjected to drained cyclic shearing, the slippage at the soil grain contact occurs, resulting in densification and plastic volumetric strain epsilon V occurs, like this, as shown by epsilon Vp. When the undrained condition is imposed, epsilon Vp has to be compensated by the same amount of the negative volumetric strain. The soil skeleton rebounds elastically to the extent required to keep the volumetric volume constant along the rebound line, like this. With the bulk modulus of water Kw being sufficiently high to ignore the volumetric change of water, the change in pore pressure can be simply expressed as a product of elastic rebound modulus ER and plastic shear strain, like this. The only two variables, epsilon Vp and ER, defines pore pressure generation. This relationship should hold true for any saturated granular material. Martin et al. Recognized the usefulness of this intrinsic relationship. They formulated volumetric strain epsilon Vp based on drained cyclic simple shear test with constant shear strain amplitude, as indicated this equation. The delta epsilon Vp is the increase in plastic strain in cyclic drained shearing with shear strain amplitude of gamma. For the field liquefaction assessment with specified liquefaction specified earthquake acceleration time history, the acceleration and shear stress has to be converted to shear strain by introducing shear modulus G gamma relation. Then another material constant to describe G gamma relation are needed. Hence, the shear strain-based model has many parameters that need to be determined experimentally. The stress-based model, although the shear strain is more clearly correlated with plastic volumetric strain than is shear stress, a stress-based model has a clear advantage over the strain-based model. In liquefaction triggering assessment, acceleration and thus shear stresses are directly used to obtain volumetric strain in the stress-based model. In this study, a stress-based model is formulated based on triaxial testing. The sand in the triaxial testing, the sand used for all the tests conducted in this study and quoted from the literature in this study was medium dense Toyura sand in a range of relative density of 45 and 51%, confined isotropically at effective stresses of either 50 kilopascal or 100 kilopascal. This shows the evolution of the volumetric strain with the number of uniform cycles of CSR in drained triaxial test. The epsilon VP increased with the number of cycles, with epsilon VP being higher for higher cyclic stress ratio. All the curves are geometrically similar and well approximated with an exponential function of the number of cycles and CSR like this. A set of 3 parameters, A, B, C, and D, completely defines the volumetric change behavior under drained cyclic shearing of the constant CSR. Cyclic stress ratio, CSR, in most conventional laboratory liquefaction tests, the amplitude of CSR is constant throughout the test. However, the actual cyclic stress ratio, CSRA, increase due to the generation of excess pore pressure. This means that in order to estimate the plastic volumetric strain for sand in unsaturated undrained cyclic shearing using the epsilon VP model, the value of epsilon cyclic stress ratio actual CSRA in each cycle should be considered even for constant CSR test. The variation in actual cyclic stress ratio from cycle to cycle is also the case when random shear stress caused by earthquake acceleration is considered. It is apparent that the sand that has already been subjected to cycles of shearing and therefore has accumulated epsilon VP exhibits a less contractive response to cyclic shearing than that of freshly deposited sand without any accumulated epsilon VP. The basic assumption similar to that used by Martin et al. Is employed in this study. The plastic volumetric strain increment for cycle of shearing depend on cyclic stress ratio, CSRA, actual cyclic stress ratio, and plastic volumetric strain accumulated at the time since the deposition of the sand, as indicated here at the red point. The independent of the number of the cycle and the cyclic stress ratio previously experienced, epsilon VP alone affect the densification characteristic of sand. For sand accumulating epsilon VP here at the end of ice cycle, the plastic volumetric strain increment delta epsilon VP at the next step, I mean I+1 step, is defined as indicated in this figure, like this. The freshly deposited sand without epsilon VP has the highest potential, as indicated in this curve at origin from origin, highest potential to densify, and epsilon VP decreases as the accumulated plastic strain increases.
Professor Okamura, I'm very sorry to interrupt you. Would you mind putting it in presenter mode, in full screen, not presenter mode, full screen, because maybe we don't see all the points you flagged.
Okay. Wait.
The bottom right button next to the little book.
Bottom right?
Next to the Zoom, to the left of the Zoom.
Slideshow. You use the slide. Yeah, you use the slideshow, Professor Okamura.
Yes, I know what you mean. Why not? I know what you mean, but
or do F5.
F5?
F5 will do.
It doesn't work.
Press F5.
Yes, F5.
Yes.
It doesn't work.
Maybe sometimes the.
Yeah. Thank you, Marty.
Sorry for inconvenience, but wait.
Yeah, that's the one.
No, I can't. So can I continue?
Yeah, I think we'll have to continue then.
Sorry.
It's still visible. Yeah, it doesn't matter.
Sorry for your convenience. Yes, the next is elastic bulk modules. The elastic rebound modules of sand ER was observed in triax testing. The specimens were isotropically consolidated to the 100 kilopascal here, followed by unloading to 20 kilopascal and reloading back to 100 kilopascal again, before and after the drained cyclic sharing. Although the rebound curve were non-linear, linear approximation was applied just for simplicity in this study. The curve was reasonably approximated by lines with ER of 24 megapascal and 13.5 megapascal for the range of this 100 from 100 to 50 and 50 to 25 kilopascal respectively. Right-hand side, this also shows unloading curves of the two specimens before and after the drained cyclic sharing. Before drained cyclic sharing, the ER was in the range of this one, about 24 megapascal. The one specimen was subject to the cyclic sharing and caused 0.4 pre-shaking volumetric strain. Another specimen was subjected to more cyclic sharing in drained condition and caused 1.2% of the epsilon BP. But even although after the cyclic sharing, the rebound modulus practically doesn't change. So in this study, in the following simulations, these parameters were used in this study. So from now on, I will present the comparisons between triaxial test observation and simulations using the pore pressure model. First of all, the normally consolidated, fully saturated sand without pre-shaking history. This shows the typical result of the observed excess pore pressure ratio, RU, during cyclic sharing. The tested specimens were fully saturated, medium dense soil sand, normally consolidated at 50 kilopascal, and subjected to undrained cyclic sharing with constant CSR amplitude. This is ordinary liquefaction test. The excess pore pressure increment for a single cycle was largest at the first cycle around here, and slow down gradually with the number of cycles. The RU increased sharply after the RU reached approximately 0.6 and finally jumped up to 1.0. The simulated RU using the pore pressure model is shown in red dots. The overall trend of RU evolution for the test observation and the pore pressure model prediction agreed quite well. The rapid increase in the excess pore pressure after the RU exceeded 0.6 is also evident for the model prediction. This shows the relationship between cyclic stress ratio and the number of cycles needed to liquefy obtained from test. And also the red line shows the model. The pore pressure model predicted the liquefaction resistance satisfactorily well. I will explain more in detail using the result of this one. This shows cyclic stress ratio CSR and actual cyclic stress ratio CSR-A for test one. CSR blue dot is constant throughout the test at 0.135, but actual CSR-A increased as excess or pore pressure increase. At point A, corresponding to the specimen before shearing, which liquefied in 16 cycles of uniform cyclic CSR of 0.135. This corresponds to point A in the liquefaction resistance curve here. At the seventh cycle, here, as indicated by B.
还有一个就是接触，
yes, here at the point B, the excess pore pressure reached the 13.5 kilopascal, and the CSRA, actual CSRA was increased to 0.185, where remaining number of cycle to liquefy was 9. This is suggested by the plot of the point B in this curve. Likewise, the point C, excess water pressure is 25, and the CSRA is 0.26, and the corresponding point is point C in the liquefaction curve out here. These red dots shows that spacement gradually enhanced to liquefaction resistance as the cyclic shearing proceeded. The resistance distance from the cyclic stress ratio, no, the resistance distance from CSR, this curve, black curve, which is ordinary liquefaction resistance curve, represents the distance from this curve to this red point represents the increase in the resistance to liquefaction, which was gained due to the cyclic shearing. This increase in liquefaction resistance is explained by Epsilon Vp, which increased gradually and decreased volumetric strain potential. The point B here and the point C here, the corresponded to the plastic volumetric strain Epsilon Vp of 0.1% and 0.2% respectively. It is interesting to mention that the contours line of the Epsilon Vp 0.1% and 0.2% in this figure, that is the line BB, and that is the line CC by the dot line, broken line, indicated to the liquefaction strength curve for sand, which was accumulated Epsilon Vp by small pre-shearing, described in this next session. The next is the behavior of the sand with pre-shearing. The traction testing by Nelson and Okamura is quoted. They conducted a series of trilateral tests to investigate the effect of pre-shearing on liquefaction resistance. The sand used was uniform dense soil sand and normally consolidated at 50 kilopascal. Weak cyclic shearing was applied in drained condition to the spacements in prior to undrained cyclic shearing until target volumetric strain Epsilon Vps was attained. For the pre-shearing, the cyclic stress ratio and the number of cycles were systematically varied in the test to achieve the target volumetric strain of 0.1, 0.3, or 0.8%. This shows typical excess pore pressure responses to the undrained cyclic shearing of the specimen with 3 target volumetric strain of 0, 0.1%, and 0.3%. Specimens accumulating higher Epsilon Vp required more cycle to liquefaction. The right-hand side, this shows the relationship between cyclic stress ratio and the number of cycles to liquefy. The pre-shearing enhanced the liquefaction resistance very significantly, although the increase in the relative density due to the pre-shearing was marginal. The pre-shearing volumetric strain was of 0.8% in this case, corresponding to only a 3.9% increase in relative density. The data point corresponding to the same Epsilon Vp lays almost on the same line irrespective of the cyclic stress ratio and the number of cycles in the antecedent pre-shearing. The pore pressure model was used to predict the pore pressure response to pre-sheared sand. The primary effect of the pre-shearing is to reduce the volumetric strain potential. You can see here the accumulated volumetric strain during the pre-shearing, indicated by blue line, was taken into account in the model calculation by introducing this amount of diffusion VP as the initial volumetric strain here. Following the pre-shearing, diffusion VP in liquefaction test increased from this point, not the origin. This shows the typical excess power pressure responses. The black dot, the red triangle, and the light blue dot indicate the result of the prediction using the model. The model simulated observed excess power pressure generation quite well. And it is of interesting to mention that the excess power pressure observed in the test increased more or less linearly with the number of cycles for pre-sheared sand, like as indicated by blue lines. While for the sand without pre-shearing sand, like black one, in the first cycle was largest and the slowdown in the following cycles. This pattern of the excess power pressure response is well represented by the model. This shows the liquefaction resistance curve both for observed in the test and predicted by the power pressure model. The model successfully predicted the liquefaction curves for the sand. It should be noted that the line for the diffusion VP of 0.1% in this figure, here in the red line, coincide with those for diffusion V of 0.1% for virgin sand, as already showed in the last section, indicated by green line. It can be concluded that the plastic volumetric strain that the sand accumulates during undrained cyclic shearing has the same effect as that gained by the pre-shearing or on reducing the potential for further densification and power pressure generation. The effect of the degree of saturation is next topic. The unsaturated sand can change its volume even if undrained condition is imposed. The volume change of unsaturated sand mass in undrained condition is equal to that of its void, which is comprised of water-air mixture. The considering of the volumetric constraint, the diffusion VP is have to be equal to diffusion VP minus diffusion VA, like here. The plastic rebound necessary to satisfy the volumetric constraint is only from point B to D. So the excess power pressure is obtained as the product of diffusion VE and ER, according to this equation. The liquefaction resistance curve observed by the structure test and predicted by water pressure model is shown here, and both they agreed quite well. The next example is the effect of partial drainage. The fully saturated toluene sand specimen were prepared and normally consolidated at 100 kPa. The 4 partial drained cyclic shear test was conducted with the rate of drainage d epsilon v dn varied from 0 to 0.005% per cycle. And the CSR was kept constant at 0.16. This shows the volumetric strain and the excess power pressure obtained from the test. The effect of the drainage on the power pressure response are very significant. The black line corresponding to the completely undrained test, and green line indicate the partial drainage test with the rate of the drainage of 0.0025% per cycle, which enlarge the number of cycles to liquefy very significantly. The further increase in the drainage rate to 0.004 or 0.005% prevented the occurrence of liquefaction and suppressed the maximum pore pressure, excess pore pressure. The dots correspond to the prediction by the water pressure model, and the model simulated quite well the pore pressure response of partially drained triaxial test. On the volumetric strain effective stress plane, you can see that the partial drainage plays the same role of air of the unsaturated sand. The dots are excess pore pressure obtained from the model. Here, the model predicts ugly quite well. Lastly, the effect of overconsolidation is presented. This shows the result of undrained cyclic test on normally consolidated and overconsolidated medium-dense soil sand derived from literature. The liquefaction resistance increased almost linearly with logarithm of OCR, like this. The tests were simulated using the pore pressure model. The specimen went through the overconsolidation process from O to A, and accumulated plastic volume strain of epsilon VP OC here. The overconsolidated specimen at point A seems very similar to that of the specimen subjected to pre-shearing specimen. In order to observe the rebound modulus ER, another triaxial testing was conducted. The specimen were normally consolidated at 100 kPa first at point A, and loaded to 400 kPa and reloaded back, unloaded to 100 kPa to this point A. And the ER was measured. It was confirmed that rebound modulus ER does not change practically, that almost the same, even though the accumulated the plastic epsilon VP OC was 0.35% was accumulated. This red line shows simulated liquefaction resistance using the model. The liquefaction resistance RL from the model increased with OCR in the similar manner to the test result, but the RL from the model overestimates the test result. An additional test was conducted to see the evolution of the epsilon VP due to the drained cyclic shearing. Medium dense soil sand was prepared with OCR of 4. During overconsolidation process, the plastic volumetric strain of the 0.35% was accumulated to the sand, like this. The specimen was subjected to the drained cyclic shearing with the cyclic stress ratio of 0.18. The volumetric strain of overconsolidated sand is smaller than that for the normally consolidated sand. However, the observed epsilon VP for OCR4 is larger than that for virgin sand with pre-shearing volumetric strain of 0.35% here. It is expected that the red line shifted vertically 0.35% here should have fallen on the virgin sand line, as indicated by blue line here. This discrepancy indicates that the plastic volumetric strain accumulated during overconsolidation process and that accumulated during volumetric strain accumulated during cyclic shearing have different effects on the densification of the sand in subsequent cyclic shearing. This might indicate that the plastic volumetric strain induced by cyclic shearing is caused predominantly by sliding at the sand particle contacts. In contrast, The sand carries normal stresses at the summit of the highest asperity of the particle surface, and the consolidation pressure increases. The significant number of the contact asperity may crash and deform plastically. The area of the contact increases, resulting in densification of the sand. This plastic volumetric strain, however, does not significantly reduce the potential of volumetric strain of the subsequent cyclic shearing. In conclusion, in this study, this study developed a pore pressure model based on stress-controlled trajectory test at a constant shear stress amplitude. The model follows the basic assumption in Martin et al. That a unique relationship exists between the volumetric strain in drained test and excess pore pressure in undrained test. The plastic volumetric strain developed during undrained cyclic shearing is absorbed by elastic rebound in the soil skeleton due to the reduction in effective stress, preserving the condition of the constant volume. The plastic volumetric strain in drained test was modeled based on the constant CSR trajectory test in this study. This cyclic stress-based model has an apparent advantage over the shear strain-based model of Martin et al. In the aspect that in the assessment of liquefaction triggering conditions, acceleration and thus shear stress is directly used to obtain the volumetric strain in the stress-based model, while strain must be converted into stress using shear modulus in the strain-based model. The effects of various factors of pore pressure generation and the liquefaction resistance of clean sand were explained using a unique index volumetric strain through trajectory tests and simulations using the proposed model. The plastic volumetric strain accumulated during isotropic loading and unloading cycles have different effects from those accumulated by cyclic shearing on the densification of sand in subsequent cyclic shearing. The ability of the model to predict the pore water pressure in pre-sheared, sheared, and unsaturated sand in undrained condition and partially drained condition was confirmed. The model has considerable benefit in improving the understanding of the effects of different factors of liquefaction resistance. That's it for my presentation, and thank you very much for your very kind attention.
Thank you very much, Professor Okamura. That was very, very interesting. I think we already have a question from the audience, from Bingo, if this is the correct name. Maybe you would like also to put your affiliation in the chat. So he or she asking whether the volumetric plastic strain due to pre-shearing is states that is a determining factor, and if the volumetric plastic strain change during pre-shaking, does that mean that the density of the sand has changed? So essentially changing the state of the sand. And in a sense, wondering whether the pre-shaking effect is the same effect as the effect of density for sand's resistance.
Regarding the pre-shearing effect, like this, the volumetric strain due to the pre-shearing is only 0.1 or 0.23 or 0.8%, corresponding to the change in relative density of sand of up to only 3%. The 3% change of the relative density in medium dense sand, say from 50% to the 53%, is maybe negligible. So pre-shearing the volumetric strain has totally different effects on the liquefaction resistance. This is the point.
Thank you very much. Are there more questions for Professor Okamura? And you can also raise your hand and so that you can ask live if you like. One for Professor Yang.
Thank you, Professor Okamura, for the presentation. So here I have questions about unsaturated case. So you measure the volume change you on the undrained condition. So can you elaborate a little bit more how you can accurately measure the volume change on the undrained condition for partially saturated specimen?
Yes, the change in the volume of the in the triaxial testing, the change in the volume can be measured using the double cell system. I mean that the change in the water level of the confining pressure cell in the very small cell can be measured and confirm that the change in volume of the air included in the specimen can follow almost very exactly to the Boyle-Charles law. So we confirmed that after confirmation of that experiment, we can easily assess the change in volume of unsaturated sand using only from the excess pore pressure. So as the excess pore water pressure increase, the air bubble in the sand shrink or reduce it in volume according to the Boyle-Charles law.
Okay, so your system is double cell system.
Yes, right.
Okay, thank you.
And not only myself, but the other research group in Japan confirmed this conclusion. Yes.
Okay, thank you.
And any other question for Professor Okamura? No. Then if that's the case, I think I understand it has been a very long day for all of you. It's the last session today, so then maybe it's a way to conclude. Just before we close the session and thanking once more Professor Okamura, I understand that Rui Wang has some announcement to make, and then maybe then we can first actually thank Professor Okamura. Thank you very much. It was a very, very interesting
Thank you very much.
presentation.
Thank you very much.
Thank you, Professor Okamura, and thank you, Professor Konto and Professor Yang for chairing the session. So I would like to thank everyone in the audience for attending the sessions today. Despite all the time zone differences that has caused a lot of difficulties.